Assalamualaikum everyone. Today our topic is Boolean functions and logic gates, and our group is group two, and the team members of my group are, as you can see, these are my team members. We have Daniyal Aziz and me, Abdullah Javed, and Saud Daniyal and Haroon Murtaza. So fundamentals of logics. We have to understand what is a preposition. So move to the next slide. As we can see, a logic foundation. In logic foundation, first we have to see the preposition. A preposition is a statement that is either true or false. A statement which can either be true or false. What does that mean? We can take a daily life example that if it rains, the streets are gonna be wet. So in which we can see if it rains, it's true statement, and if it rains, it affects the other statement, which is like the streets become wet. So this is a statement, a logical statement, and basically this is an informal statement. So I'll go towards the formal and informal topic. The informal statement is a daily casual like statement that if it rains, the street becomes wet. This is a really informal statement. So in computational logic, in logics, we changes this statement into a P implies Q. So the if it trains become P, and which implies that the uh, the street becomes wet. This becomes your implies that the P is affected by Q and Q is affected by P. So this shows the basic relation in our formal statement, in our logic, and this is a bedrock of logic contradictions. So let's move to the next slide. So we have tautology, and it means which is a statement which is always true. Here we can see that if T is true and we have put a OR gate between T and not T. Not T means that it is the opposite of T. So if T is true and the opposite of T will be false. So if we take an OR gate, in OR gate we just need one true statement, so the output is always true. So this is our basic tautology concept, that when one statement is true, the other is always true, and the output that we have come across is always true. So this is the concept of tautology. Now we'll go to the next slide. So this is contradiction, which is always false, which means that a statement that is always false, and this will happen when we will take a true statement and we'll have an AND gate between it and the opposite of that statement. So as you know, the outputs for an AND gate to be a true is always should be the statement should be both statements should be the true statement. So the output will be true. But in this case, we can see if NOT gate is applied to a true statement, the output will be false. So when we will put an AND gate between them, the output will become false. So this is the basic concept of contradiction. Now we'll move to the next slide, and which is contingency content dependent. So in this we have the basic concept that the neither statement is true or false. This becomes a question, why do they are neither true or false? Because they are dependent on the logic, because they are dependent on the scenario which is happening. So in this statement we can see the example that P and Q. So in this, we can see that it is raining and I have an umbrella. So here they are both inputs. It can be true or either false. We cannot have an umbrella. We can have an umbrella, and it can rain, but it can also not rain. So this is a contingency statement, and it is always scenario based. So this is the basic concept of the contingency. So that's all from my side. Now I'll call Daniyal Aziz for his topic of presentation, and he'll introduce himself and start his presentation. Thank you.
Assalamu alaikum everyone. My name is Daniyal Aziz and today I will presenting a part of our discrete structure project. In this presentation, I will explain two important concepts of propositional logic, logical equivalence and equivalence identities. These concepts are widely used in mathematics, computer science, programming, and digital circuit design because they help us simplify logical expressions and solve problems more efficiently. So let's begin. First, let's discuss my first slide, logical equivalence. Logical equivalence means that two logical statements always produce the same truth values under every possible condition. In other words, even if two statements look different, they are considered logically equivalent. If their truth tables are exactly the same, the symbol used for logical equivalence is statement P and three lines statement Q. This statement means the statement P and statement Q have identical logical meanings and always same result. We have a real life example. Consider this statement: it is not true that the light is off. This statement also can be written as the light is on. Although the wording is different, both statements represent the same situation. Therefore, they are logical equivalent. Uh, Now we are now move to the importance of logical equivalence. Logical equivalent is very useful because it helps simplifying complex logical expression. It reduces the complexity of digital circuits. It improves program efficiency in computer science. It makes problem solving easier in mathematics and logic. Therefore, logical equivalence allows us to replace one statement with another equivalent statement without changing the final outcome. Now we will move on to our next slide, equivalence identities. Equivalence identities are the set of logical rules that help us simplify logical expression, just as algebra has formulas for simplify mathematical expressions. Proportional logic has equivalence identities for simplifying logical statements. Let's discuss some important identities. Identity law. The identity laws state that combining a proportion with a neutral value does not change its original meaning. First identity, P and T, logical equivalence P. This means that when a statement is AND with true, the result remains the original statement. For example, I am a student and true still means I am a student. Now we move on to a second identity, P and P or false, logical equivalence P. This means that when a statement is or with false, the result remains the original statement. For example, I am a student or false still means I am a student. Uh, Now we move on our second law, domination law. The domination laws shows the certain values completely determine the result. First domination law, P or T, logical equivalence T. Anything or with true always become true. For example, it is raining or true will always be true regardless of whether it is raining or not. Second domination law, P and F logical equivalence F. Anything and with false always becomes false. For example, it is raining and false will always be false. Now we move on our third law, double negation law. The double negation law states not not P logical equivalence P. This means that applying negation twice returns us to the original statement. For example, consider this sentence: I am not happy. After removing the double negative, it becomes I am happy. The meaning remains exactly the same. Now we have a conclusion of this topics. To conclude, logical equivalence helps us determine when two statements have the same logical meanings and produce identical truth values. On the other hand, equivalence identities provide important rules for simplifying logical expressions. These concepts plays a significant role in discrete mathematics, computer programming, digital logic design, and circuit optimization. Thank you. That's from my side. Now I would like to call Haroon Murtaza for the rest of the slides. Thank you.
My name is Haroon Murtaza, and now I will explain De Morgan's law, which are important rules in Boolean algebra and digital logic design. Actually, these laws help us simplify logical expressions and other digital symbols efficiently. So next. So first lies the negation of and become R, and each variable is individually negated. For example, if we set P 1 and Q 0, then P or Q is equal to 1 or Q. So right side, then negation of P and negation of Q, it's also becomes 0 and 1. So both sides become equal. It's easy trick to remember it is that not move inside, and the AND operator changes into OR. Next law is the negation of OR become and each variable is individually negated. So it's also the same procedure as of law 1. Next. Then the truth table of De Morgan law. This table actually provide the proof that De Morgan's law, the both sides of the De Morgan law are equal. So if we notice this table, we see that two columns are exactly the same. Then where De Morgan law is used, it is used in AND gates and in OR gates. It is useful in K-map and simplify our logic circuits. And that's all from my side. Now I would like to call Saud for next.
Assalamu alaikum. My name is Muhammad Saud, and from here I will present further. So we have Boolean algebra and circuits. So I'll discuss first what is Boolean algebra. So Boolean algebra uses binary systems. Binary system is the foundation of computer science, and it is used in widely in electronics. Like it deals with binary numbers, zeros or ones, because the computer only knows two conditions, two states. Either it is 0 or it is 1. Either the switch is open or it is closed. So it was Boolean algebra was given by George Boole. He was the founder of the Boolean algebra. It is a foundation of computer science. It is used in digital circuits. Like in digital circuits, we can use in logical gates like AND, OR, NOT, NAND, etc. And also in computer science. Computer science, we have in programming like if and else conditions. We can use if this or else that. In databases, we can also use it in databases. Databases uses the logic of AND operators and OR operators. Also, we can use in search engines. These are the applications that are applied in Boolean algebra. Now we have logic gate circuits. So we have three basic logic gates. These are OR, and NOT. As you can see there, this is OR, and we have a NOT gate also. So the functionality is that AND gate accept two inputs and gives only one output. It gives the output 1 when both of its inputs are 1, and 0 when any of its input is 0. While on the other hand, OR gates is somewhat like AND but completely different. Like if we have either input is 1, then the output will be 1. But if both the inputs are 0, then the output will become automatically 0. NOT gate is also called an inverter gate. It inverts the input which is given to him and gives the opposite output. Like if A is 0, then the output will be automatically become 1, because it inverts the 0 input into 1. Then we have here are the symbols and operator. And for AND gate, we have dot operator. It means P and Q, and OR gate we have plus operator, which means P or Q. And for NOT gate, we have a complement operator, which says it inverts the input. Then we have universal gates. In universal gates, we have NAND gate and NOR gate, because by combining the basic gates like AND gate and NOT gate, sorry, we can make another gate which is NAND gate, or we can combine NOT gate and OR gate to make another gate which is NOR gate. Then we have functions and simplification. Here in this, what is Boolean function? Well, Boolean function takes two inputs, any input, number of inputs, and gives a number of outputs. Let's say, for example, we have a function here, f of a, b, and c. We can define this function as a and b or c. Here the dot means and the plus means or. So according to this function, we have two terms, a and b plus c. It means we have two terms. Either of its inputs are 1, then the function will automatically become 1. So we can also simplify Boolean functions using the help of some laws that are given to us, like complement laws, identity laws. For example, we have a function here, f of a dot b plus f of plus a dot b complement. Here we can see there are three gates used. First a dot b, then b or a, then a dot b, and then a complement gate, which is a NOT gate. We can simplify this function by, we can see that in two terms, there's something in common, which is a. We can factor a and we will remain with b plus b complement. We can use the complement law, which states that b plus b complement equals to 1. Then here it will remain only 1. Then we'll have with a multiplied by 1. The identity law says that anything multiplied with a 1 equals to a. So the result we will remain with is f of a. Here we can see we will initially we have 4 gates, but after simplification we will use only none gate because the simplify law states that. Then the efficiency in real system. Why do we use simplification and why do we use Boolean algebra? We can minimize the level of circuits, like reduces fewer gates. Like I discussed in previous slides earlier, that initially we have 4 gates and after simplification we can use only 1 gate or 0 gate. That in that case we can use fewer gates. Fewer gates means the complexity will it will be less complex and more simpler, improve speeds, and also it will in terms of cost, it will in less cost, it improves speed, saves power and energy. It can also be implemented in mobile embedded apps and IoT things. So that's it from our side. If you have any questions or any queries, you can ask in comment section from any part of the presentation. If you don't understand any part, you can ask in question in the comment section. Thank you for watching and thank you for time.